Hi, my name is Clarissa Kozrak, and today I'll be walking through an example use case demonstration for automobile fleet predictive maintenance using Amazon SageMaker. Amazon SageMaker helps data scientists and developers to quickly prepare, build, train, and deploy high-quality machine learning models by bringing together a broad set of capabilities purpose-built for ML. We'll be working in SageMaker Studio for this demo. SageMaker Studio is a fully integrated development environment for machine learning, making it a great tool for rapidly iterating through the building, training, and deploying of machine learning models. For our predictive maintenance demo, the example notebook focuses on binary classification using a SageMaker built-in algorithm called Linear Learner in order to predict vehicle failures. The repository containing the example notebook, dataset, and additional documentation can be found in the link in the description box. In order to follow along, you will need to clone the example repo and download the datasets. The industry use case we'll be covering is predictive maintenance. Now, what is predictive maintenance and why is it important for businesses? Predictive maintenance is a proactive strategy for minimizing machinery maintenance downtime by predicting machinery failures. Some of the main goals for predictive maintenance are 1. To reduce operational costs by optimizing the time and effort needed to repair machinery, and 2. To minimize unexpected downtime due to machinery failures. Predictive maintenance allows for businesses to proactively address equipment issues, thus reducing unnecessary expenses, boosting scalability and productivity, and increasing transparency into production. When machinery breaks down, it negatively affects a business's efficiency, productivity, and growth. With the adoption of machine learning, you can create actionable insights and extend the remaining useful life of your machinery at the lowest cost and improve operational efficiency. For our use case demo today, we'll start off by briefly exploring SageMaker Studio, then transition to preparing the fleet dataset using SageMaker Data Wrangler, and finally walk through an example notebook for predictive maintenance. This will be a great opportunity for data scientists and developers new to AWS and SageMaker Studio to explore some of these SageMaker features in action and be able to quickly create their own predictive maintenance solution to fit their business needs. Note that for this demo, you will first need to create an AWS account, and you will also need to create an S3 bucket. And with that, let's get started. Great, so once you open up SageMaker Studio and the Launcher tab is open, you can see that the launcher has a variety of different features and quick start methods that you can use to get up and running with SageMaker Studio. You could try using the SageMaker Jumpstart or use Autopilot, which will quickly create a model automatically. And under ML tasks and components, you have the ability to leverage some of the new features from SageMaker. So first off, we have new feature group, and new feature group is a new Amazon feature called Amazon SageMaker Feature Store, and that will connect with Data Wrangler. And here we have a new data flow, and for the new data flow, this will leverage the SageMaker Data Wrangler feature, which we will actually walk through in a bit. You also have the ability to jump right into using a Python 3 notebook, and you can select a new notebook, and you can select which SageMaker image you want to use by selecting this dropdown and picking from this list. To start off, we will go to our file browser by selecting the icon in the top left-hand corner. And here we can see any folders or notebooks that are available to us. Here you can see I have the AWS Predictive Maintenance repo already cloned right here. And just as a note, you will need to clone the AWS Predictive Maintenance repo and upload the datasets to S3 in order to follow along with this tutorial. There are also a few other additional icons on the left-hand side that I'm going to walk you through. So under the file browser, we have Git, and this is actually where I cloned the Git repository needed for this tutorial. And you can initialize a repository here as well. Under Git, we have the running terminals and the kernels. So if you select this tab, you can see here that we have our running instances, our apps, and our kernel sessions. And this will tell us exactly what is running, the size of the instances that are running, and then also we have the ability here to kill any of the instances, sessions, or running apps if needed. So the last tab I'm going to walk you through is the SageMaker Components and Registries tab, and that's this bottom one down here. And here you're able to select the different components or the registries that you want to view. So if you select the drop-down, you can see that there are projects, data wrangler, feature store, pipeline, etc. And this is a really great tool to be able to navigate and toggle between the different components and registries within the SageMaker ecosystem. So for our purposes, if we select Data Wrangler, we can see it gets populated with the Data Wrangler flows that have already been created. I have 3 here that are other flows not related to our project, and then we have this PRM predictive maintenance.flow file. So if we go ahead and select the flow file, we open up and get this data flow for our Data Wrangler job. And I've mentioned Data Wrangler before, but what exactly is SageMaker Data Wrangler? Well, SageMaker Data Wrangler is a new feature that simplifies the process of data preparation and feature engineering. It allows you to complete each step of the data preparation workflow, including data selection, cleansing, exploration, and visualization, all from a single interface, making data preparation quicker and easier. I'll start by walking us through the data flow for the predictive maintenance use case demo. And as you can see here, I have already imported the data from our 2 sources. So we have our source here, which is from S3, and this is the example fleet info.csv, as well as the other object in S3, which is example fleet sensor logs.csv. When you're importing data into Data Wrangler, you have the option of selecting between a variety of different sources. So for our purposes, we used S3, but you could also select through Amazon Athena or other Amazon sources. Both of these data sets are coming from my S3 bucket called SageMaker Fleet Predictive Maintenance Solution, and you will need to create your own S3 bucket and load the data sets into it in order to use the Data Wrangler flow. A little bit more detail about these 2 data sets. So the first one is example fleet info.csv. Example fleet info.csv is fleet data information about the vehicles such as make and model and their engine types, and it has other information about the vehicle fleets as well. The second data set is the example fleet sensors log.csv, and this data set includes all of the sensor log information for each of the vehicle's engines. Within Data Wrangler, you have the ability of using 300 built-in data transformations on your data, and you can use all of them from this convenient visual user interface. Within Data Wrangler, you also have the option of creating custom transformations using PySpark, SQL, or Pandas. We can do things like encode categorical variables or deal with missing data or outliers. We can add or remove columns, and the list of possible transformations goes on and on. Now that I've given you a brief introduction to SageMaker Data Wrangler, I'm going to walk you through this Data Wrangler flow for the use case and go into a little bit of detail of all of the different steps for the flow and show you how I exported the file. Some of these steps are going to include things like encoding categorical columns, renaming columns, reordering the data set, and joining both of the data sets together. This is less of a step-by-step process and more of an overview of the flow. To start off, we can look at the data types for example fleet info.csv and inspect the data set a little bit. So we select data types, and here you can see again that the example fleet info CSV is mostly attributes of each of the vehicles. So we have the make, the model, the year, vehicle class, and engine type. And if we go back to the data flow and select the data types for the other data set, here we can see that we have the vehicle ID again, which will be needed for a join later on. We have the target, and then we have timestamp, which our timestamp is every 2 hours. And then we have voltage, current, and resistance. And voltage, current, or resistance, these readings are taken every 2 hours. If we hop back to the data flow, then in steps parentheses 4, we can select the bottom and code categorical. And from here, we can see that we have previous steps 6. And the 6 steps are to import the data sets, look at the data types, and change them if needed, like we just did. And then we have these 4 encode categorical steps. So as we saw in the previous step, we have the make, the model, year, the vehicle class, and the engine type as our fleet vehicle info. And All of these except for year are considered non-ordinal. So we can create these encode categorical steps and using the one-hot encode transform as opposed to ordinal. We select our input column. So I did this for make, model, vehicle class, and engine type. And then I decided to keep the invalid handling strategy as keep instead of skip or error. And finally, I changed all of the names to be the original name. In this case, it's engine underscore type and then underscore code. From there, if we go back to the data flow and look at the transform step for manage columns, from here, we can see that we had 3 previous steps, which were the importing of the data, the looking and the changing of the data types, and the managing columns. And here for manage columns, I just went ahead and changed the name from timestamp to datetime. And I did this because the datetime column will be needed for the notebook later on. So going back to the data flow, the next step is to join both of the data sets. And I will go ahead and skip over to the steps parentheses 5 and hit the bottom manage columns. And if we go to previous step 6, the first step is this join. So I'll select the join and we can inspect it a little bit further. So you can see I did a right outer join. I joined both the vehicle ID and vehicle ID from both of the tables. And from there we get a merge table that has both of the vehicle ID columns still in it. We have vehicle ID 0 and vehicle ID 1, and that is because those are the join keys and they keep both of the columns. So I went ahead and dropped the vehicle ID 0, changed vehicle ID 1 to vehicle ID, and then I moved the 3 columns, target, datetime, and vehicle ID to the front of the dataset. One thing to note here is that these datasets are generally pretty clean because they're generated data. So there are not a lot of transformation steps that are done for this use case tutorial. But I encourage you to explore some of the additional transforms that you can do under the add header. You can add custom transforms, such as using PySpark or Pandas or SQL. And you can also add in custom formulas or encode variables differently. You can featureize text and format string. So I encourage you to explore more of the transforms that are available and even use some of the transforms for analysis. So once we're done with these transformations, we can go back to the data flow, select Analyze, and under Analyze and the steps parentheses 5, we can go down to Manage Columns where the chart icon is, select Manage Columns, and this will take us to our analysis pane. So here we have all of the different Analyze charts that we've created thus far. So we select the vehicle age distribution. You can see here that the analysis populates, and from here we can see a snippet of the table. We can also see the selections that I've made. So here I've created a histogram called vehicle age distribution, and we are looking at the age of the vehicles, and it's going to be colored by the target. So from here we can go back to analysis, and by selecting create new analysis, we are opened up to a new analysis pane where we can create a new analysis chart. So here we have the option of either using the configure options, such as any of these drop-down charts, or we can go into code and create our own chart based on Pandas data frames. Or we can come here to create our own chart using a Pandas data frame. So for purposes here, we'll go to configure. We will select table summary and rename the analysis summary stats. And here we have a populated table summary of all of the different summary statistics for our data set. So you can take advantage of this and look into some of the different summary statistics and explore your data set earlier on. And then once you are done looking at here, you can select create, and you will have created a new table summary, and here you can see all of your analyses. Once you're all done with your analysis, you can select export. export, and it will take you back to the data flow. From here, you select the final step. So for ours, it's going to be step 5, manage columns. And then you'll see that on the right-hand side, we have this export step pop up. So we'll select export step, and here we have the option of exporting our data flow as a data wrangler job, a pipeline, Python code, or feature store. And just to remind you, feature store is a new SageMaker feature. So we have the ability here to export our data flow as a feature store feature group, and that will add the features to either an offline or an online feature store. For our purposes, we are going to use the data wrangler job as our export. And I've already gone ahead and done this. So once you select this, you will be taken to a new notebook that will be your data wrangler export. And here's mine. And the only things to note here that I changed and that you would need to do as well if you're going to follow along with this tutorial step by step is that under parameters, I have gone ahead and added in the bucket as my bucket name. I've also used the magic store for bucket, and I've also changed the name to dw_output_prefix, and again stored the dw_output_prefix. So both of these stored variables will be used later on in the actual notebook, so you'll need to change those on your end to make sure that you have all of the right steps for this tutorial. And that's it. So we made it through all of the SageMaker Data Wrangler steps. You've heard a little bit about what Data Wrangler is and how you can leverage it for this demo, and also how you can start playing around with Data Wrangler for your own data sets. So now that we're done here, we're going to flip over to our actual notebook and get started with our demo. Now that we have finished our walkthrough of the SageMaker Data Wrangler flow, we can go into the AWS Predictive Maintenance repo and open the Linear Learner Fleet Predictive Maintenance notebook. Once you're in the example notebook, you can see that there is a mix of documentation and code in Python. This Python code can be run in entirety, or you can run it cell by cell. We will actually walk through a pre-run version of this notebook so that we can see all of the outputs at once. Although this notebook has commentary throughout, I highly recommend going back to the repo and reading the README Markdown file for more information and additional background about predictive maintenance. There you will also find an architecture diagram. So the example notebook that we're going to walk through today is using a SageMaker built-in algorithm called Linear Learner in order to predict for vehicle fleet failures. Predictive maintenance is a useful use case for a wide reach of customers. There are many types of predictive maintenance solutions, such as anomaly detection, remaining useful life, when you predict how much time is left before the next failure, or fault classification, when you are predicting whether or not a machine will fail within a predicted time frame. For the purposes of this use case, we will approach this problem as a binary classification problem for fault classification. For our first attempt at solving our fault classification problem, we will leverage the SageMaker built-in linear learner algorithm, which can be used for either classification or regression. With this algorithm, you can simultaneously explore different training objectives and choose the best solution from a validation set. You can also explore a large number of models and seamlessly select the best model to deploy. Another advantage of Linear Learner is that it's very fast and allows you to iterate through modeling in an efficient manner. As with many classification problems, one of the biggest challenges for predictive maintenance is data issues, in that there is generally a class imbalance issue, meaning that there are far fewer examples of failures compared to non-failures. In most cases, there are fewer failures than non-failures because businesses don't generally want to allow for more failures just for the sake of having more failure data. Another issue is that failures could be inaccurately labeled, which could also cause there to be fewer failures in the dataset. Class imbalances can make fault classification problems more difficult, so that's something to be aware of and think through as you're going through this use case. The overall flow in this notebook will be to first set up our notebook with SageMaker, download our clean data from SageMaker Data Wrangler, then do some additional data cleaning and feature engineering. Then we will start the modeling section by first creating a SageMaker experiment. We will then build our linear learner model, train the linear learner algorithm, do hyperparameter tuning with SageMaker automatic tuning job, and finally use batch transform to deploy our best model and get inferences on our test dataset. Now that we've gone through the background of the Fleet Predictive Maintenance Notebook, we can start with the setup. If we scroll down, we can see with many SageMaker Studio example notebooks, the setup is pretty consistent. As I mentioned before, you'll need an S3 bucket and you'll need to set up an IAM role for SageMaker and for data permissions. In this cell here, I have added in a magic store, and you can retrieve the stored variables from previous sessions if you want to pick up the notebook and run part of it and then return to it later. And down here, I've also imported the necessary libraries. We'll also be using the high-level SageMaker Python SDK to allow us to easily work with Amazon SageMaker and call its APIs in a data science-friendly way. Here I've added in the bucket, which is SageMaker Fleet Predictive Maintenance Solution. You will want to replace this with your own S3 bucket name. During this setup, we will also install and import the newest version of SageMaker Experiments as well as Boto 3. After we have completed our setup, we'll move on to the data preparation of the notebook. So we saw before with SageMaker Data Wrangler that we were able to load in our two data sets, change our column data types and our headers. We were able to join the data sets together, do some preliminary analysis, and create some transforms for our data set. And finally, we were able to export our data flow as a SageMaker Data Wrangler job. Now we will be able to pick up where we left off by downloading the process data from SageMaker Data Wrangler and reading the data into Python using pandas. So in this section of the notebook, we will be downloading the dataset from SageMaker Data Wrangler and reading all the CSV files into a pandas data frame. Once the dataset is loaded into a pandas data frame, we'll add in some additional features and change some data types before reordering the columns so that the target column is first, as that is necessary for the linear learner algorithm. So here we add in our additional features, we've changed our data types, added in the vehicle class, engine type, and engine age features as categories, and finally reordered. Again, it's important to note here that the dataset we're using is generated vehicle fleet data based off another AWS Labs repository. Thus, the datasets are pretty clean and require minimal cleaning. In a more normal predictive maintenance solution and pre-processing necessary in order to get the datasets in a state ready for modeling. So once we've made all of those changes and take a closer look at our data set, we can see that the data contains the target, the vehicle ID, and date time of each of the sensor readings, as well as the make, model, year, vehicle class, and engine type. We also have the sensor readings, which are voltage, current, and resistance, and all the features that are related to the engine's performance. We have made a few initial features, and after some exploration, we will create some additional time series features. Some of the observations are that we can see that the dataset has 9,000 observations and 43 columns. And we can also note that the vehicles can be identified using the vehicle_ID column. And each of the vehicles has 100 rows associated with them. Each row represents one timestamp with 3 sensor readings. We also know that the label column called target is the indicator of failure, where 0 is no failure and 1 is a failure. Next, we can plot some visuals and do some initial analysis. As I mentioned before, this is a class imbalance problem, so we can see here that there are about 19.6% failures compared to about 80-ish non-failures. So this is definitely more of a class imbalance problem. In the next cell, we can evaluate the percentage of failures by the vehicle ID. We can see that there are no missing values and none of the sensor readings are giving us 0 values, which would be an abnormality for this data set. Once we've finished up our data cleaning and our initial analysis, we can move on to our feature engineering. So if we scroll down to the next section, we get into the feature engineering. And for our purposes, we will create some time series features and use categorical labels that we created before. We're just going to focus on getting the lag for voltage, current, and resistance. And we will focus on lags because with time series data, we know that the sensor readings at time t are probably related to the sensor readings at time t-1 and t-2, etc. We will also want to create rolling statistics for voltage, current, and resistance and group them by vehicle ID. The statistics we will focus on are mean and standard deviation. Once we've created the rolling mean and rolling standard deviation for our window, then we'll join the new columns with the fleet dataset. And that's what we get here. We can also take one more look at the summary statistics, as seen here, and also look at some of the plots of the histograms for the different features. Once we've finalized our feature dataset and saved it to CSV, now we can move on to training. I mentioned before that we are treating our predictive maintenance sensor readings as time series data, so we'll want to split our train, test, and validation sets based on time, and also take special care to make sure there is no data leakage. Here we will devote 80% to training, and we'll save 10% for 10 and about 10% for validation, keeping in mind that the validation dataset will have slightly less records to avoid the leakage from overlapping dates. When we are happy with our train, test, and validation sets, down here we will upload our train, test, and validation sets to S3 and begin our modeling. From here we'll use a couple of additional SageMaker features. We will use SageMaker experiments as well as SageMaker automatic model tuning and batch transform. So moving on to train, we will start with SageMaker experiments by creating a SageMaker experiment called LL for linear learner failure classification create date. We'll store the experiment's name for future use, and throughout the rest of the notebook, we'll create trial components for each of the models, and we will evaluate and add them to the experiment. So here we have our try except to see if there's an experiment by that name, and if there is, go ahead and use that experiment. Otherwise, we'll create a brand new experiment. Scrolling down, by similar logic, here we will create the trials. If there is a trial that goes by that name, then we will use that one. Otherwise, we will create a brand new trial. Throughout this notebook, we will be training multiple models. And to start out, we will first initialize an estimator for logistic regression. There are a number of components that we will need to set up, such as the image URI, the IAM role, and the number of instances and training type that we will want to use, as well as the output paths per SageMaker session. You can change the configuration or keep the configuration and the hyperparameters the same as they are in this cell currently. Here there are a number of parameters that we can set as well. We will set the predictor type to binary classifier and type of loss to logistic. Finally, when we are fitting the model to the data, we will add an experiment configuration that loads the algorithm container, loads the data from S3, trains the model, outputs the model artifact to the S3 path that we passed in earlier, and tears down the training cluster once it's complete. One thing to note here is that our inputs are actually going to be the S3 paths we created above. We will pass in the path to our training datasets as well as the path to our validation dataset. We do this because linear learner requires the path to S3 as opposed to passing it in an array as you would when you are building a model with something like sklearn. Now I already ran this cell and I trained the model, but I received the output logs here in blue. You can view these logs and monitor Amazon SageMaker using Amazon CloudWatch. Amazon CloudWatch collects raw data and processes it into readable near real-time metrics. These statistics are then kept for 15 months, so you can access historical information and gain a better perspective on how your web application or service is performing. So since I've created multiple models in this notebook, I'm now going to skip ahead to the next section. So once we've created the several different trials and trained multiple models, we can compare and evaluate these models against each other and move on to the hyperparameter tuning for one of the models. In addition to the logistic regression model that we walked through, this notebook also trains a support vector machines model, and we will use that model for our hyperparameter tuning job. We will first set up a hyperparameter tuning job, and with SageMaker hyperparameter tuning, we can set this hyperparameter tuning job for a number of different hyperparameters. SageMaker hyperparameter tuning will automatically launch multiple training jobs with different hyperparameter settings, evaluate the results of those training jobs based off predefined objective metrics, and select the hyperparameter settings for future attempts based off the results. We will define the maximum number of training jobs as 20 down here, and we will also set the number of parallel jobs as 2. Up here, we'll create the tuning job name and we'll store that name. We will again set the output path in the container and create the tuning job. Now the hyperparameter tuning job does take quite a bit of time, so I'm going to pause here and I will meet you when it's done. Great. So once the hyperparameter tuning job is done, we're going to go ahead and associate the hyperparameter tuning job with the SageMaker experiment. This is an optional section of the notebook, so I won't go into too much detail here, but if you're interested in doing this, you can go to the notebook and step through each cell. From here, we'll move on to the prediction portion. We're going to get inferences for an entire dataset using batch transform. With batch transform, you create a batch transform job using a trained model from our hyperparameter tuning job above. We will use our test dataset, which is stored in S3, to get predictions on. Amazon SageMaker saves the inferences in an S3 bucket that you specify when you create the batch transform job. Batch transform manages all of the compute resources required to get inferences, meaning that batch transform handles launching instances and deleting them after the batch transform job has completed without any extra steps from us. So starting here, first we'll get the best model from our tuner above, as well as the batch input, which is the path to our test data. Once we have created our transformer, we'll actually get the batch inferences by calling transform and passing in the batch input, the content type, so here it will be a CSV, and the split type, which will be line, so that it's splitting each row of the test data set. If we run this cell, again, we will get logs, and we can check those logs in CloudWatch, as I explained above. And once the batch inference is done, it will automatically upload the output to S3. Next, we will evaluate our results by downloading the results from S3. The results will come in as a JSON file, and I've created an evaluate model helper function here that will take in the batch file path, the test labels, as well as the model name. We will parse the JSON file to get the predicted label outputs, and from there we calculate the evaluation metrics such as accuracy, recall, and precision, and F1. Finally, we get all of the different metrics as well as the confusion matrix. Finally, we can go ahead and move on to the cleanup section. The cleanup is optional, but we can go ahead and delete all of our experiments, or we can just clean up individual experiments. You can go ahead and delete the unused or unneeded experiments, or you can keep all of the components up and running. Just know that there will be a cost associated with keeping the components of this tutorial running. There are some additional resources and extensions at the end of this tutorial. You could continue to evaluate the hyperparameters and tune them to improve the model. You could try more of a tree-based model to deal with the class imbalance piece, such as SageMaker's built-in algorithm XGBoost, which is commonly used for predictive maintenance. And finally, once you've created a model and are happy with the results, you can actually extend this tutorial by deploying the model at the edge using Amazon SageMaker Neo and AWS IoT Greengrass. There is an additional example of deploying a predictive maintenance solution at the edge linked in the end of this notebook. And there you have it. We've explored SageMaker and its features and walked through a demo of vehicle fleet fault classification. Until next time, happy developing!